You know that feeling, right? That little jolt of anxiety when you hit save on something really important.
Oh, definitely. Or make an online purchase.
Exactly. Or you just close a browser tab after filling out some long form, and you expect that information to just be there, safe, permanent.
hmm We take it for granted.
We totally do. But how often do we really stop and think about, the digital magic that actually makes that happen?
Hmm.
How does our data survive a system crash or like a sudden power cut?
Or any number of other weird disruptions that can happen.
Right. It feels like this invisible guarantee we just rely on. So today, we're going to dig into that guarantee. This deep dive is all about data durability.
It's a concept that honestly doesn't get enough credit. It's kind of an unsung hero.
Totally. And for anyone familiar with database stuff, it's the decadent AC atomicity, consistency, isolation, and durability, a fundamental promise.
The bedrock, really.
So our mission today is to, pull back the curtain on this. We're going to explore the clever mechanisms that make sure your data actually stays safe no matter what digital chaos might be going on. Okay, let's unpack this.
Okay. So data durability, at its heart, it's the principle in database management that guarantees the permanence of transactions once they're committed.
Committed meaning like saved successfully.
Exactly. Once the system says, okay, I've got this, data durability is the ironclad promise that this data will survive. It'll survive crashes, power failures, you name it.
It's basically the assurance that once accepted, it's, etched in digital stone, right?
Pretty much. It's not going anywhere.
That sounds incredibly important. But beyond the tech definition, why is this permanence so critical?
Yeah.
What's it really protecting us from? Why should someone who isn't, a database architect care?
Yeah, that's a great question because the implications are huge. They really touch everything we do online. There are, I say, 4 main reasons it's so crucial. First, and probably the most obvious, is data integrity. It basically prevents your critical information from being lost or corrupted.
Like your bank balance suddenly changing after a glitch?
Precisely. Or important documents just vanishing. Durability is the safeguard against that. What you save stays saved, exactly as you saved it.
Makes sense. What's next?
Second, it's fundamental for user and business trust. Think about it. When you make a payment or upload something important, durability is that quiet promise that your action is permanent.
Right, you trust the system will remember it.
Exactly. And that trust is what makes the digital economy, social media, everything actually function.
Yeah.
Without it, things would just fall apart.
Okay, integrity and trust. Got it.
Third, durability is absolutely key for system recovery. When things inevitably go wrong, and they do, durability gives systems a predictable way to get back to a stable point.
So they can return to the last known good state.
Precisely. It minimizes downtime, ensures things can keep running. Super important for everything from, power grids to online shops.
Okay, that's critical for keeping things running. And the fourth?
And finally, it's crucial for compliance and auditing. Lots of industries have really strict rules about keeping data, think legal, financial, medical records.
Right, regulations.
Exactly. Durability ensures organizations can meet these data retention requirements. It provides that secure, permanent record needed for legal reasons, audits, or just accountability.
Wow. Okay, so integrity, trust, recovery, and compliance. It's actually kind of amazing how much relies on this one principle working correctly behind the scenes.
It really is. Every time we use a digital service, we're placing our trust in its durability.
Yeah, it's definitely not just a tech detail, it's foundational. So if it's that critical, how do databases actually achieve it? How do they make data permanent against, all sorts of potential problems? What's going on under the hood?
Well, the main workhorse, and it's quite clever, is something called write-ahead logging, usually just called WALO.
Write-ahead logging.
Oh.
Okay.
Think of it like keeping a meticulous diary before you actually change your main records. Before any change hits the actual database files, it's first written down in a separate, special log file.
So it logs the intention before doing the action.
Exactly. It's a sequential record of every change that's supposed to happen.
Okay, and how does that help if, say, the power goes out mid-change?
That's the beauty of it. If the system crashes before a change is fully written to the main database, it doesn't matter that the main file might be incomplete or inconsistent.
Because the log.
Because the log has the record of what should have happened. On restart, the system reads the log and can replay those transactions that didn't fully complete. It brings the database back to a consistent, correct state.
So it's like an instruction manual for recovery. It ensures nothing committed gets lost,
Yeah.
even if the main writing process was interrupted.
Precisely. It guarantees atomicity and durability for transactions.
Okay, wall sounds smart for handling transaction integrity. But what if the whole server just dies? Or, whole data center has an issue. Is wall enough then?
Good point. No, wall protects the data on that server. For bigger failures, you need another layer, and that's where replication comes in.
Making copies.
Basically, yes.
Okay.
Copying the data across multiple servers, often in different places. This gives you redundancy. If one server fails, another one has a copy of the data.
Makes sense. Are there different ways to do this copying?
Yes, primarily two main flavors, synchronous and asynchronous, and they represent a classic trade-off.
Okay.
Synchronous replication is all about maximum safety. When you save something, the transaction isn't confirmed back to you as done until the system gets confirmation that the change has been successfully written on all the servers involved.
So every copy has to acknowledge it first.
Correct. This means if the primary server fails, you know for sure that an identical up to the second copy exists elsewhere. No data loss.
But I'm guessing there's a catch.
The catch is latency. It takes longer because you have to wait for all those confirmations. So it's a bit slower, but it's the gold standard for safety. Think financial systems.
Okay, so what's the alternative? Asynchronous.
Right, asynchronous replication. This one prioritizes speed. The primary server writes the change, often confirms it back to you immediately, and then it sends the change to the secondary servers in the background.
So it doesn't wait for the copies to confirm?
Nope. It makes the operation feel much faster to the user. Great for things where you need quick responses, like social media feeds or high-volume logging.
But is there a risk?
There's a very, very small window of risk. If the primary server crashes right after confirming to you, but before the change got sent to a secondary, then that tiny bit of data could potentially be lost.
Okay, so faster, but a tiny possibility of loss in a worst-case crash scenario.
Exactly. It's often perfectly acceptable for many applications where that slight risk is outweighed by the need for speed. It leads to something called eventual consistency, where the copies eventually catch up.
That distinction is really clear. It shows there's no single right way, just different choices depending on what you prioritize. So we have wall, we have these replication strategies. Are there other tools in the durability toolkit?
Oh yeah, definitely. These work together with other techniques. For instance, you often hear about journaling.
How's that different from wall? Sounds similar.
It's very similar in principle, recording operations for safe replay. Often journaling is talked about more in the context of file systems, ensuring metadata consistency, whereas WAL is very specifically about database transaction logs. But the core idea, recording before committing, is the same.
Okay, so related concepts. Anything else?
Yeah, periodic checkpointing or snapshots. This is really important for recovery speed.
How so?
Instead of having to replay the entire log from the dawn of time after a crash, the system periodically saves the entire consistent state of the database to disk. This is a checkpoint or snapshot.
Like a save point.
Exactly, like a save point. So after a crash, the system can load the latest checkpoint and then only needs to replay the logs since that checkpoint. Makes recovery much, much faster.
Got it. So it's really a combination of things, logging changes, making copies, taking snapshots, all working together.
Absolutely. It's a layered defense, a whole set of strategies to ensure that data sticks around.
It really highlights the complexity involved in building systems we rely on every day. But, there's usually a catch with powerful tech. There has to be a balancing act here, right? We focused on safety, permanence. Where does durability potentially cause issues or require compromise?
You're spot on. There's a fundamental trade-off between durability guarantees and performance. It's one of the biggest challenges for system designers.
How does that play out?
Well, the stronger the guarantee you want, like synchronous replication everywhere, forcing every write to disk immediately, the more work the system has to do. More disk writes, more network messages, more waiting for confirmations.
And more work means slower.
Slower, yes. It generally leads to higher latency, meaning each individual operation takes longer, and it can reduce throughput, which is how many operations the system can handle per second overall.
So maximum safety can mean reduced speed and capacity.
That's the core tension. It forces architects to make really strategic choices based on what the application actually needs.
Can you give an example?
Sure. Think about a financial system again. Processing payments, stock trades, whatever. Here, data loss is absolutely catastrophic, often illegal.
Right, non-negotiable.
So they will configure for the strongest possible durability. They'll accept the slightly higher latency because the integrity of the data is paramount, Performance is important, but safety comes first.
Okay, that makes perfect sense. What about the other end of the spectrum?
Contrast that with, say, a high-traffic social media app. You're posting updates, liking things, sending messages constantly, billions of tiny operations.
Yeah, it needs to feel instant.
Exactly. User experience demands speed and responsiveness. While they definitely don't want to lose data, maybe losing a like notification in a 1 in a billion crash scenario is an acceptable, tiny risk compared to making every single interaction feel sluggish.
So they might use asynchronous replication, maybe relax some disk flushing rules.
Precisely. They optimize for low latency and high throughput, providing very good durability, but perhaps not the absolute Fort Knox level of a bank. It's a different balance, tuned for a different purpose.
That's a great comparison. So when my banking app feels super secure, but maybe a fraction slower, and my social media feels instant, it's not just my internet. It's these deep architectural decisions about durability versus performance.
Absolutely. Those choices about logging, replication, consistency levels, they directly impact how that service feels and behaves for you.
It really drives home how much thought goes into making these systems work the way they do.
And it raises that interesting question, doesn't it? For all the different systems we use, where do we as users actually want that balance point to be? It's different for different things.
That's a good point. Well, this has been a fantastic deep dive. We started with that little worry about hitting save.
Yeah, that moment of hope.
And we've really journeyed through the world of data durability. We defined it, that guarantee of permanence for committed transactions. We understood why it's so critical: integrity, trust, recovery, compliance. Then we look under the hood at how things like write-ahead logging, synchronous versus asynchronous replication, checkpointing.
The whole toolkit.
Right. And finally, we tackled that crucial balancing act, the trade-offs system designers make between absolute safety and, raw speed.
And stepping back, you see that data durability isn't just some obscure technical feature. It's really the invisible scaffolding holding up our trust in the entire digital world.
Yeah,
It's what lets us click buy or send that email or save that document with confidence, knowing it's actually been recorded and preserved. It's the silent promise.
that's a great way to put it, the silent promise. So maybe the next time you hit save or send a message or make that online payment, just take a second. Appreciate the incredible unseen engineering making sure it sticks. It's pretty amazing, really.
It is a testament to clever design.
So what other systems do you rely on every day that depends silently on these kinds of guarantees? Something to think about. Thanks so much for joining us on this deep dive.